Very specific about the kind.
I see. Yeah, kind of the same thing they tell us up here just about.
It's like, so you're taking a space heater that's not very hot.
Yeah. Well, looks like we can get started. Welcome back, everyone. Before we start work for today, any questions or comments? Okay, yeah, go ahead.
So just so we're clear, if we dress up for Halloween next week for this class, we don't get any extra credit.
You don't get any extra credit?
Yeah, if we like wear a costume for Halloween to this class, we don't get any extra credit for doing that.
Oh, I see what you're saying. Yeah. You know, we could put an extra credit assignment on there.
Really?
Yeah, why not? So I'll put something on Moodle here that says, come in with some form of costume. I'll actually give extra credit. And if you're only on Zoom, maybe it snows real bad, that I can pull out the, there's a camera somewhere. There it is. I could pull out the camera and just double check that way. So yeah, why not? We'll put it as like an extra credit assignment. Let me write something down. Halloween. Extra credit. I usually cancel that class, but they get pissed when I do that, and it's not a night class. So we have to be here. We'll make the best of it. But that'll be my reminder. And I'll make it some form of extra credit that's tied in with the quiz grade or something along those lines. Well, other questions at the moment? Thanks for asking about that. Okay. Well, other things to mention is definitely it feels like we're getting really close to winter already with the snow that we got. So just a reminder, if you had a hard time getting to class today, if roads are really bad and you have to travel far, then there's always going to be recorded lectures posted here on a day-by-day basis. You can always find those and see what class you might have missed. They have dates and sections on them to kind of identify which is which. And also, if you think that you're just not going to make it, but you still want to participate in class live, just send me an email before class asking for a Zoom link, and I'll be very happy to send it over to you. So you're welcome to join by Zoom if there's really bad roads. And if you miss class, maybe internet goes down, anything can happen with bad weather. It'll be recorded here. If it's missing, it pretty much means we didn't have class, or maybe the technology down here just screwed up really bad and we couldn't make it happen. But for our announcements for today, we're now in section 5.6. We're on example 2, part C. And our brand new quiz is highly based off that example 2. I would look at example A, B, and C before starting off that quiz. But in my opinion, it's most similar to part B of example 2 for that 10th quiz. Then after we finish section 5.6, well, we'll see where we end up today. We're not going to try to speed through it. We'll go to 5.7 on inverse and radical functions. And this is pretty much going to be our last section in chapter 5. This one's a pretty short review section. We've already covered inverse functions, but we're going to focus on the new functions we've been picking up, like the rational functions and so on. So before we jump into the notes, also take a look right here. On the day-by-day syllabus, we've been pretty close to what the intended goal was, but 5.6, that was probably not realistic to finish it in one day after exam 2, because here we are on this day, and we're still in section 5.6. What that means is I'm going to remove section 5.8 from the actual coverage. That one was on variation. It's a pretty cool topic, but if I'm being honest, that's the one topic in here that I would consider fluff in the schedule. To get a little bit behind, we had to kill that section. So that section is going to be dropped off, and 5.7 will be the last one of chapter 6. That means we're going to do section 2.7, which goes along with a section 6.1 topic right after. Oh, where am I here? Right after the 5.7 on inverse functions. So that's the announcement so far, folks. Any questions about any of those at the moment? Okay, and I guess I should just restate for folks coming in. There is a Halloween extra credit opportunity if you'd like to come in with any kind of costume or decoration or Halloweeny makeup, then I'll award some form of extra credit. I don't know exactly how that's going to work, but I'll make it official by putting a write-up here sometime after class, probably on Friday. Well, other questions or comments at all, folks, before we begin our work? Okay, well, let's jump into 5.6, and this is exactly where we left off on. But really, before jumping into this problem, we also made one extra promise about this theorem right here. It's a super important theorem, and while we were looking at it, we just scribbled all over it. So if you want a clean version to print out, that's this right here, horizontal asymptotes. So once again, probably the most important theorem in this entire section, because it's going to tell us essentially how all the horizontal asymptotes must look like depending on our situation. So if we go to section 5.6, here's the problem that we left off on right here. Now let's just go through the motions. It's kind of a review / warm-up problem. We did a couple of these already. We want to find x and y intercepts, equation of all asymptotes. Then we'll sketch our asymptotes using dashed lines. So let's start off with the easier things to find. If you want vertical asymptotes, I'll write V for vertical, ASY to stand for asymptotes. Then you're just looking to the denominator. You have to write your answers as an equation, x equals. That way we're knowing we're dealing with an actual vertical line. But you're just finding the value that would make denominators go to 0. You're finding the excluded values from the domain. So right here, you'd get x equals -3 for one equation. And from right here, you would get x equals +1. So if you think of how you would find the domain of that function, those would be the two values not in your interval notation. So of course, vertical asymptotes are done. Next thing we have to take a look at are vertical asymptotes. Excuse me, horizontal asymptotes. I think I said that backwards. Let me try again. Vertical asymptotes are those two. Now let's go to horizontal asymptotes. Before we just jump right in, we need to know the degrees. So let's say here, degree of the numerator. Anyone see what that overall degree would come out as? Exactly. If we were to FOIL this all out, we would get an x squared term as the highest power. So it's a degree 2 in the numerator. And by the same reason, degree 2 down in the denominator. So we'll say down here, the degree of denominator is equal to 2. That means we have a tie. And if we have a tie, all we're looking for is the leading coefficients. It's a little bit tricky on this because we haven't expanded the numerator nor the denominator, but you can still read off what leading coefficients are right in this format. So the way I'll show it is, first I'll expand it just to show what it would look like if you went that route. Then I'll show what the shortcut would be if you decide to skip to the punchline. You can do this either way. So first, let's just expand things, both numerator and denominator, h of x. I'll do the expansion first of x plus 2 times x minus 4. We'll get x squared minus 4x plus 2x minus 8. So that's our numerator so far. Then same kind of deal in the denominator. We'll get x squared minus x plus 3x minus 3. At this stage, we can pretty much see leading coefficients, but wouldn't hurt to take one extra step and clean this up a little bit. We can distribute through and get 2x squared. Now it's kind of lazy. I didn't even combine these like terms. Let's do it right here. -4x plus 2x is -2x. 2 distributes, and it becomes -4x. Then 2 multiplies that -8, giving us a -16. And now we can combine like terms down below. It's x squared plus 2x minus 3. So we have a leading coefficient of 2 in the numerator. And the leading coefficient in the denominator would be a coefficient of 1 that we see right here. We can insert it if we just really need to look at it. But that's the shortcut. This 2 here gave us a leading coefficient of 2, only because there was no numbers around this x or that x. When you FOIL all that through, you just get a 2x squared. Likewise, multiply all this through, and you'll just get an x squared. So my shortcut kind of just looks like this. That produces the 2x squared in our two-way tie. Down below, that produces the x squared. So we can say for horizontal asymptote, let me actually color code these just slightly different. Because it's a horizontal line, it has to start off as y equals. Then we go up above, pull the coefficient from the leading term up top, it's a 2. Coefficient from the leading term down below would be a 1. Same as this 2 and 1 we got from right over here. And that's our horizontal asymptote. Looks kind of funny left in that form, so I would probably say y equals 2 is my official answer, but I wouldn't be super picky about that if you left it in that format. All right, we have asymptotes, a vertical one, a horizontal one, and only because we saw the tie, we knew exactly what to do with this one. We pretty much just used part 2 right here. The degrees were equal. So we took essentially what would be a 4 in this problem, a -5 down below, and formed the horizontal asymptote in that way. So we'll call on this theorem again as needed as we work through these problems. But any questions at all, folks, on finding those 3 asymptotes at the moment? Yeah.
So for the horizontal asymptote,
Mhm.
how did you get the 2 over 1 and the 2 again?
So when we expanded all of this right here, it became 2 times that group. And then we got the 2x squared when it distributed through. So that's where the 2 came from. Essentially this location, which was pulled off from right up here. But then when we got the 1, we FOILed all this out and it first turned into just that altogether. But there's still a number multiplying x squared. We just inserted a 1 times it, and that's where we got our 1. Yes, good call, absolutely. Honestly, when their functions are in this nice factored form, you can pretty much eyeball everything all at once, like you're mentioning. We have a -2, +4 for zeros right away. Other questions or comments so far? Okay, well, let's go to the zeros next. If we're finding the zeros, we're really dealing with x and y intercepts. So let's say here, for x intercepts, we go back to the function up here. And now we just care about that term, excuse me, that factor and that factor. The intercepts are just going to be ways the numerator can turn into a 0. From right here, you would just plug in a -2. Put in, oh, let me try this all over again. I always forget I have a marker going. If you put in -2 right here for x, the whole entire output is now 0. Does that make sense to folks on that input? Awesome. It'll cause a 0 in the numerator, no zeros down below. And so that's one x-intercept, or a 0 like you mentioned earlier is a great way to say it. Then up here, plug in a +4. The output is going to be 0 right where the red dot is. And so now the entire thing is 0. So those are our x-intercepts, -2, 0, 4, 0. The next thing we want are going to be the y-intercepts. And for a y-intercept, that's pretty quick too. I would start by always writing this for a y-intercept because it reminds us we're plugging 0 into that overall function. So we're pretty much focusing right here, go h of 0. And let's do this carefully. Plugging 0 in for x is going to give us 2 times 0 + 2, 0 - 4. Down below, here it's going to be 0 + 3. And a 0 - 1. So this should simplify pretty rapidly. It's now turning into 2 times 2 times -4. So it looks like -16 in the numerator. Denominator is 3 times -1, so -3. And now we get 16/3 altogether. So we take that output right here, go back to your y-intercept, and here's the 16/3. Well, these problems are kind of busy after a while because we have a lot of information we have to summarize before we even start plotting this thing. So just for the sake of showing where all the results ended up, let me box my answers here. The real goal is to try to find a way to write your results that you never have to box things. You can just find them easily. But if it feels like it's just too busy, never a bad idea to just indicate those were the things that we're trying to find. And now last thing to do is that bit of instructions right there. We need to sketch the overall graph using all that information. So here's where the graph is going to go. Before we start plotting things down, any questions or comments at the moment? Okay, best strategy after you came up with all this information in the boxes is really put down your asymptotes. Those are the guidelines of the whole graph, so it's a great place to start. Vertical asymptotes are real barriers you can't cross. So we have one at -3. Oh, I kind of missed that tick mark. Let's just make it bigger. So here's the equation x equals -3. There's one at +1. So here's the equation x equals 1. And by the way, when you put these dashed lines here, you don't necessarily have to say the equation. It doesn't hurt to do it. But when you're reporting the vertical asymptotes and horizontal asymptotes, you do have to say this part. Since determining which is which, it does depend on actually writing the equation with the equality and putting in the right variable, x versus y. So those are the two asymptotes that are vertical. This one's horizontal at height 2. So it comes through like that. So here's y equals 2. I'd say after you have your asymptotes down, let's plot our intercepts next. We'll have one at -2, 0. So an intercept in this location. Next one is at 4, 0. So 2, 3, 4. Here's our next intercept. And that's powerful information right here. These are the only two places your graph can ever cross. If it does something weird and crosses somewhere else, it had a bit of mistake somewhere in our work, because those are our only two intercepts. Now that one's a little bit of annoying, but 16/3, let me just put this as scratch for the moment. 16/3, 3 goes into 16/5 with remainder 1. So it's really 5 1/3, and I'll try to plot it as that number. So up 1, 2, 3, 4, 5, 6. Right about there is where I'd say 5 1/3 ought to land. So that's our y-intercept in that location. All we have to now do is produce the entire graph. Let me copy this. We're probably going to need the function as we go through this, because occasionally we still need to find some test points to make sure we're plotting the curve in the right location. For example, in this region, to the left of x equals -3, I don't necessarily know if it's up here or down there. All I know is it has to approach y equals 2, this dashed line right here. So let's plug in a value of, let's see, that's -4 right here, and just see what happens to the function. So h of -4, we'll have 2. Next, it's -4 plus 2, so that'll turn into a -2. Here it's -4 minus 4, so we've got a -8. Down below, now we have -4 plus 3 for a -1. And this will be -4 minus 1, so now -5. So let's take a look. There's 4 negative signs, so our overall answer is positive. That means we're somewhere over here then. Also, when we go to simplify this, this looks like 4 by 8, so 32 fifths. 5 goes into 36 times, remainder 2. So our point at -4 should be 6 2/5. Up here is 6, so I just need a point slightly higher. That ought to do. Doesn't have to be perfectly plotted. Remember, we're not trying to do a picture perfect plot, just try to capture the important information on the plot. So now we know the curve lies up here. From here, it has to be attracted to the dashed line at x equals -3. And then coming down, it's attracted to the horizontal line, y equals 2. So that's 1/3 of the way done. If we have 2 vertical asymptotes, we need to find the graph on 3 different places. So now we're between both vertical asymptotes, wondering what the curve will look like in this region. Any questions first, folks, on getting that first branch of the curve? Okay, let's keep on plotting. The middle branch here is not too bad. We for sure have to go through here, and so we can make it go, say, like this. It will be attracted to the vertical asymptote coming in on the left. Then we have to cross through here. That's the y-intercept. So let's make that happen. Comes up, crosses through, but now it's attracted to that vertical asymptote at x equals 1. So this one's not too bad. And here, because we have an intercept right there, we know the curve is below y equals 2. I would finish off the rest of the sketch by pretty much just doing this. Goes off in that way and then shoots down in that kind of way. Curve looks a little bit shaky in this region, but that's okay. It could be, as long as it conveys the right information, asymptotes, intercepts, and it's not doing anything weird like invalidating the vertical line test, then you'll always get full credit on these kinds of curves. But again, every time you do this, especially if it's a quiz problem or maybe an ALEKS problem, you have extra tools available to you. So I encourage you, grab a graphing calculator, whether it's a TID4, something more fancy, or something on a browser. It's always good to just check this out, see if we're on the right track. Let's make that our next step here. Got to move those windows around. So first step is just type in that function, h of x equals 2x plus 2, x minus 4. It's kind of fun how the curve updates in real time as you start typing this out. Then divide by x plus 3, x minus 1. So our curve should have looked about like this. I'd say we did a great job. I'd probably also add one extra thing, the horizontal asymptote, because that's tricky. It had a 3-part theorem to make sure we landed on the right one. We said it was y equals 2. Yeah, it's doing the right thing. Curve is attracted on this end and on this end, just like what we see over here and over here. So we've got it, folks. That's a tough sketch. Let me take a look. Right in that location, I think that would still be in the domain. So offshoot of it. Well, that value, say, right over here is where you're pointing at, right? Well, it has a value. It's at negative 1.25. You have a height of 2. Does that make sense with that point there? Gotcha. Other questions or comments so far, folks? Okay, well, we did it. Pretty much what happened with this second example is we went to this theorem and we did all 3 parts. 1, 2, and 3 are just different problems on this example number 2. And when it comes time to doing a quiz problem, again, I mentioned quiz number 10. I believe it's pretty similar to part B, where you actually have to factor it. And on the final exam, this is a question to always make it onto the final exam. Oh, one moment, I think we've got an open mic. There we go. And on the final exam, again, it's probably going to be one of these 3 versions that we saw right here. Some of them we have to just go right at it, like this one. Other ones we were required to factor it. And sometimes on the final exam, they give you a factored form like this one, just to speed up the exam. And that way it's not going to be too long to get through. So it all just depends on who writes it to this time on the math department. Let me get rid of that. That was just for a quick reference. And again, these are the pretty routine problems. Now we're getting to some of the trickier things, like this one right here. It was definitely pulled right out of ALEKS. And just like when we were doing polynomials, it's one thing to take an equation like this and graph it, but it feels like an entirely different process if you go from the graph to an equation. So now we're fully reversing everything we just did in that very last problem. So let's give this a try. It's kind of overwhelming too, because ALEKS has a way of just throwing a bunch of stuff at us that isn't really necessary. What I would do when I solve this problem is I would just ignore this for the moment. I mean, we still need to use it. We have to answer the question. But at the moment, it's just a bunch of noise. It's easier to find the equation of the function first and then return to this pane. So I'll unscribble it at the moment, but ignore it for the moment when you see it at the start. Let's read through the problem. It says, figure below shows a graph of a rational function f. It has vertical asymptotes at x equals 1, so that's that asymptote, x equals 5. They tell us a horizontal asymptote, y equals 0 as well. That's pretty interesting information, because if you have a horizontal asymptote, y equals 0, we can go back to this theorem. And this is the only way, where are we? There we are, part 3. This is the only way you get y equals 0 as your asymptote. It had to be that the degree of p of x was less than the degree of q of x. So let's pull this out just in case we need it. I'll drop it down there just for the moment. So having a horizontal asymptote is definitely good information, but notice it also shows a intercept right here. So this is one x-intercept. That's good information too, because when we find an x-intercept, that always comes out of the numerator. If there were two intercepts, then we found, like in this case, intercept here and here. That means there was two factors in the numerator. There's just one intercept. There should be just one factor in our numerator. So that's pretty good information already. Let's see if we can start writing out the function. We can say f of x equals, let's focus on that x-intercept. It's at -5, so we can write x plus 5 in our numerator. And that ought to be our almost entire numerator. Let's put this value here. A, we're going to have to deal with later. There could be a number multiplying that numerator. We had a 2 in just the last problem we did. But does that make sense to folks on why put an x plus 5 here? Okay, pretty much it's just the opposite of that coordinate there, that first coordinate. So if you plug in a -5, yep, you'll hit 0 right here exactly. Now let's go to the x-intercepts next. They were at 1 and at 5. Let's give this a color that stands out a bit. Once you have that information, that's going to go into the denominator. That's how we get our vertical asymptotes. We just see how the denominator goes to 0. So down below, if it's a positive 1 right here, we'll go x minus 1. And if it's a positive 5 here, we'll go x minus 5. So far, that's our equation. All we need to do is solve for the value a right here. And the way we do that is, for the one given point they gave us, that's got to be used some way, somehow. If you have a point like this, it's also saying that f of 7 equals -2. So you can always break down a coordinate on a graph into function notation like this, which is helpful because we have a function right here. That's what's going to allow us to solve for the last piece, that value a. Well, let's work through this equation, get our a value, and then we'll take a look at this, see if it's correct. Already it looks pretty great, right? We had a horizontal asymptote at y equals 0. Degree of the numerator is 1. Degree of the denominator would be 2. And so, yeah, degree of the top, that's the p of x, the thing on top, is less than degree of q of x, the thing on the denominator. So I think we're done with that there, but we can leave it here for the moment. Now let's work through this. F of 7 equals -2. That means we're coming back over here, plugging in a 7 for all the x's. We'll have a 7 plus 5 divided by 7 minus 1 times 7 minus 5. That's set equal to -2. And now this is an equation for which we can solve for a on. That's a pretty fast equation. Let's just simplify those parentheses. In the numerator, it's 12a. And in the denominator, it'll be 6 times 2. All set to -2. And that's just a coincidence on this problem. 12 has automatically canceled with the 12 down below. And so a equals -2. So we can come back over here, fill this in and say, therefore, f of x equals -2, x plus 5 divided by x minus 1 times x minus 5. That's pretty much how the whole problem goes. But now we have to answer the question. That's where I think Alex is a little bit annoying here. I think they're trying to give hints of these are the possible formats that could come up. And we have to select the first one that matches our situation. We're on this line. We had an a times x minus something divided by 2 different factors. So I would just fill that in. Then you have to fill in all these boxes, but you're really just importing that information. So it would go like this. -2, x plus 5, x minus 1, times x minus 5. I'll write it that way since I don't think I can actually squeeze that into the space they give us here. So that's how that ALEKS topic goes. In my opinion, I think this is the trickiest one because we're reversing everything on it. But if you can really need to learn a process in the forward direction, like doing this, because it's probably a final exam question, you can get a very good understanding of this direction by inverting it. And that's pretty much the whole punchline to this problem. It reinforces doing the normal problems if we start doing them backwards like this one. Well, we've got it, folks. This one had a particular equation, and it's never a bad idea to do this. Let's do it one more time just to emphasize. Before you click the submit button on ALEKS, just check it out. See if your equation even makes sense based on their graph. We have f of x is -2, x plus 5, x minus 1, x minus 5. So this graph, let's take a look. Yeah, it looks pretty much the same. We could match up points if we'd like. We have -5, 0. And what's that? Oh, that's not a 0. It's just an interesting point there. And we had some other values like -7, or excuse me, +7, -2. Let's see if we can hit that value. It's really hard to hit. Oh, there it is, 7, -2. So at this stage, I'd be convinced we've got the right thing, and I'd hit enter on ALEKS at that point. So any kind of graphing calculator like that, it could save dozens of minutes off this assignment, potentially half of hours. Well, any questions at all, folks, on doing any of these kinds of problems so far? Okay, I'd consider this the main topics that we got through so far in this section. So congratulations. I think this one is the next trickier section after that zeros of polynomial functions that we got through. There's still some interesting problems that are inside here. And this is the next interesting problem. Slant asymptotes are just another variety of asymptotes that can come into play. And occasionally in the homework system, that's something we'll be looking for. And here's how a slant asymptote could come into play. Let's take this function right here and make a slant asymptote actually happen. The denominator is degree 2. The numerator is of degree 1. If we up the degree, now we have a horizontal asymptote. But if we go up even higher, now we have a slant asymptote. And that's a pretty good name. It's slanting up in that direction, almost like a linear equation. So the idea behind this is, if the numerator is of degree 1 higher, exactly 1 higher than the denominator, you will have a slant asymptote. Let's put that here just for the sake of making that comment available. If the degree of the numerator is exactly 1 higher than the degree of the denominator, the function, let's say the rational function, just to be specific, will have a slant asymptote. So watch out for those in the ALEKS problems. They're tricky just to spot that that's what they were asking for on those kinds of questions. This is how you'll spot it right here. Now we're going to find a slant asymptote down below here, but just for the sake of illustrating what we're about to do, let's read through this and see just what happens. It says here, we have a function h of x indicated in this way, so a good old rational function. The degree of the numerator is 2, degree of the denominator is 1, so it satisfies that condition. It will have a slant asymptote. Then what we do is we take 3x minus 9 and we'll literally long divide that thing to get this as a result. But this is the result of long division. This wouldn't be synthetic division since I have a coefficient there. You could try to factor it out or just use ordinary long division on that thing. But here's what's going to happen to this. As the absolute value of x gets larger and larger, meaning a very large positive number or a very large negative number, this thing is going to get closer and closer to 0. The reason for that is that's a rational function as well. And we can say here, the degree of the numerator is 0, degree of the denominator is 1. It matches that condition. The degree of the numerator, the top is less than the degree of the denominator. So it has a horizontal asymptote of equation y equals 0. So this part right here gets closer and closer to 0 as x gets large. That means the whole entire function begins to look like this, 2/3 x for very large values of x, either positive or negative. So that's the whole idea with the slant asymptote. And let's try it out right here and see if we can make this happen. Any questions or comments first, folks, about the weirdness that's happening right here? Okay, I felt like it's a good write-up to put on this because just giving a definition of a slant asymptote really becomes cryptic. We have to see it actually happening. So even better than the definition is us working out ourselves. So let's give it a try down here. So right away, if you're told to do these instructions, be very, very suspicious. Sure, it has a vertical asymptote at -3. It doesn't have any horizontal asymptote. And if we give Alex just that information, we lose the question. They're looking for a slant asymptote on this one, and they don't necessarily say it. It's kind of rude. So watch out for that information there once again. Let's maybe go down the line. Question first, sorry.
Yes, so if there's not a horizontal asymptote, will there always be a slant?
Not necessarily. Say, for example, if the degree of the numerator is exactly 1 higher, you'll have a slant. But if we make the degree of the numerator even higher than that, let's go say power 4, then it goes back to just some weird arbitrary rational function. It won't have a slant asymptote in this case. Other questions about that so far? Okay, so in this problem, the only reason it had a slant is degree of the numerator is 2, degree of the denominator is 1, so it satisfies this condition. Now let's go down the line. We focus on the denominator temporarily. We can say we have a vertical asymptote of equation x equals -3, taking the opposite of that value down below. Then when we compare degrees, we'll say here, degree equals 2, down below, degree equals 1. And this tells us there is no horizontal asymptote on this graph. But once again, this implies there is a slant asymptote. So let's go and find that slant asymptote, and that's going to satisfy this question here. They just wanted us to sketch the graph, plot asymptotes, and so here's the next steps. We're literally just going to long divide this thing. I'll use synthetic division since this is a nice function to use that on. Take the opposite of the 3 there. So let's just keep that color coding, why not? So here's the -3. Then we put a little bracket here, a tally bar down below, and pull coefficients from the numerator. They go 1, -1, -20. Now we're ready for our process. This one carries on down. Multiply that 1 by -3. It kitty corners over to this location. And then tally again, -4 here. Multiply by -3, we'll have a +12 now. Take the sum, we'll get a -8. And now with that information, it looks cryptic, but we've done the long division. We just have to say it. So this f of x is now equal to, let's see here. I like to put in x squared just to remind me what the degree was. Then the degree down below is 1 less, and we'll put in x minus 4 minus 8 divided by still that x plus 3. So this is the remainder, and this is the value we got from right here, that our quotient itself. Now, we're about ready to get our slant asymptote. We can say as the absolute value of x gets large, the function f of x becomes approximately equal to this right here. This quantity goes to 0 because once again, it has a horizontal asymptote at y equals 0. meaning the numbers just get smaller and smaller, the larger your denominator becomes. So f of x is approximately equal to x minus 4. And we can say here, this is the slant asymptote. But we did it. We just have to plot the rest of this graph here. But any questions at all, folks, on producing that equation right here? Okay, so long division's kind of wild. It has lots of purposes, and finding asymptotes, specifically slant asymptotes, is a really good purpose here. We're next going to try to sketch the whole graph. So we have a vertical asymptote. Let me put in boxes the information we need. We just found the slant asymptote. So next, oh, that's highlighted really weird. I'd say we ought to go for, let's say, our x and y intercepts and get a really fast plot. Let's put this on the next page just so it fits though. Okay, so back to this function. For the rest of the work, we really ought to factor it a little bit more. Let's say f of x equals, factorization of that could be, let's try x minus 5, x plus 4. The -5 and +4 will multiply to the -20. They'll add up to the -1. So that's a quick factorization for numerator. Denominator is still just x plus 3. But from that factorization, we now have the x-intercepts, and we'll get the y-intercepts just as fast. So right here, x-intercepts. We'll go take the opposite value of this term to get 5, 0. Over here, plug in the opposite value. Oh, my red dot's moving too much. Get a -4 and 0. Last one for a y-intercept. We'll plug a 0 into the function and get a result out. So I'll put my work down below. F of 0 is going to be first a -5 by the red dot. We'll multiply a +4 and be divided by a +3 when we plug in 0 for those x's. So we get -20 thirds altogether. Let me fix that 0. So -20 thirds right here. I'll put that in a box just as a reminder. When we go to get the plot, these are the 3 different elements we're going to need. The 2 sets of asymptotes, and this right here are intercepts. So now finally, we just need to put it all together and sketch out that graph. Any questions or comments at the moment, folks, to this stage? Okay, so down below right here, I think we can get it all in. That's kind of hard actually, but we'll just scroll up to see the vertical asymptote as needed. So first, vertical asymptote was at -3, like we wrote right here. So go left 1, 2, 3. And there it is. Next, we have a slant asymptote. Let me rewrite it as y equals x minus 4. And you can think of this as slope-intercept form. The slope is 1, the y-intercept is at -4. So we need to drop down 4 units. Here's where it intercepts. I'm going to put a tiny dot there, but I don't want to make it too big because it's not a point on the graph. It's just going to be the asymptote that we're graphing here, the slant one. Then the slope is 1. So from this point, go up 1, right 1. So here's up 1, right 1. Here's my second really light point. And also, if we plugged in +4 into this function, we would get a 0. So it also has to connect through right here. I plugged in 4 for x, got 0 for y, so that's the next point. The only reason I did that is I want to try to get a nice straight line. It looks kind of bad at the moment. Let's see, can we fix this? Should really kind of look like that. And I'd say that would work out for us. My scale is not perfect. If this was an exam question, we'll have graphic paper, so it's less of an issue. But I'll just let this be my line right here. So this is equation y equals x minus 4, the slant asymptote. The one above right here, this is the equation x equals -3. Let me just kind of make that go through a little bit better. And now let's plot our intercepts. We have 1 at 5. So this is now points on the graph we're putting in. 1 at -4. And man, this is going to be a hard one to plot. Let me see. Oh, geez. I think I might have to put this on the next page just to make it all fit in here. And also fix -4, 0. Didn't want to come along for the ride. Let's put a note here that this continues. I didn't make enough space on my graph. I need a little bit of a region here to plot it and make it look believable. So let me carry this down even further and even further this way. Okay, I think it'll work better now once we start to plot this. So here's how the plot goes. Let's start, oh, I forgot that value. So -20 that'll be -6 2/3. So that's our y-intercept. Lots of little details here. So we're down to -4, -5, -6, -7. So there's the y-intercept at that location. Sorry, we shouldn't forget the y-intercept, just as important as the others. Now, finally, after all that hard work, here's what my plot would look like. I'll start here. It has to be attracted to x equals -3, so it goes up in that way. And then it comes down and starts following the slant asymptote in this direction. Then, in this section of the curve, it comes up and around, connects through that y-intercept, then starts to approach this last asymptote as it connects through the x-intercept. That's going downwards towards the vertical asymptote here. Notice there's nothing in this region. Does that make sense why? Kind of tricky to see it away. And honestly, when I go to plot these, it feels like I almost missed something here. But if you did try to put something in, say if you wrote a graph that went like that, please delete this if you did write it in. It would be a mistake because now we've violated the vertical line test. There's 2 intersections here. There should have only been 1. So my claim is that's what the function should look like. Should we test it out and see if that's what we're really getting? Okay, let's give this a try. But finally, this is the whole work. And I'd say the major takeaway point of this entire problem was really right here in this box, finding that slant asymptote. But here's our last graph. Let's see if we nailed this one or if we have to go back to the drawing board. It could happen. So this time the curve is x minus 5, x plus 4, x plus 3. And you know, mine looks kind of crappy, but it's got the same sort of features that we're looking for. Intercept at -4, intercept at 5, and that's -6 2/3, it looks like right here. Only thing I haven't put on is the actual slant asymptote, and we ought to do that just to make sure we really have it. Our slant asymptote is x minus 4. And it looks like it's doing what it should be doing. Our curve gets closer and closer to the purple line, the slant asymptote, as x gets large negative, as well as when x gets large positive, it's also attracted to the slant asymptote in the right-hand side, like we were attempting to plot right here. So that's rational functions. They're weird things, and they are pretty tricky to plot. But these notes, I'd say this is going to be the big theorem to be ready to go with. And occasionally watch out for this, mainly for ALEKS problems. There can occasionally be a slant asymptotes like on this one that we have to find. Well, we did it, folks. This is a good moment to kind of pause and catch our breath before going to the next topic. Any questions or comments at the moment? Okay. The next comment I put in or topic was one of these little ALEKS problems. They just seem to be everywhere. I would love to be able to delete them because they're not on quizzes, they're not on exams, and it requires a graphing calculator. So it's kind of an odd problem. But I guess they are good problems since it's good to know just how to deal with these things numerically when you have to. So I'll leave it up to the class. Should we try to use the ALEKS graphing calculator for another topic? Okay, let's give it a try. So a slight pause while we go and get into this Alex system. We could get faster at this. Oh, there it is. Yeah, we're in section 5.6. And this one's in part B that I found. Let me know if you find other weird things there that I just missed. To me, this is the weirdest one for only reason because of the graphing calculator. There it is. And here's how it goes. It's a word problem apparently, but not really in the spirit of what a real word problem should do. But it tells us we have a function indicated by D, and this is going to be density in grams per cubic centimeters of an object X years after its origin. What in the world? Oh, studying an object in space. So X years after its origin by the following equation. Not really too sure what this experiment is about, but if we have a function, that's okay. It wants us to do the following. Find the value of X that minimizes density, find the minimum density, and then say something about what happens when X gets very, very large. Like we mentioned before, you don't have to use their graphing calculator right here. You can use any calculator. But let's do it again just to see how it goes. We'll click right here, and this is the tedious part, typing it all in. I think we've said this before. I wouldn't use their tools right here. I would just use an ordinary keyboard. Hit division right away to produce a fraction. You can go over here and just type in X plus 15. Down arrow for the denominator, 16x squared. Right arrow takes you out of the exponent, minus 48x plus 40. And that's small on my screen. Are folks able to see that all right? Okay, just double checking. It's actually kind of hard to see just on my screen down here. So once we have everything imported, it's a good idea to double check we have the numbers in, right? Then just hit graph. So there's our graph, and yeah, there's a peak on that graph for sure. Click on the find extrema. Let me click cancel. It's this one right here, extrema. That's if we're finding minimums or maximums. And you have to move these around or it may not actually even work. You have to tell it what range to find minimums and maximums. Click on find extrema, and we're just talking about maximum. So anything that talks about min, we have to ignore. Let's focus right here. The max, oh, I can't actually select those. The max is right here for X, right here for Y. Kind of rude that they don't let us copy paste on those. That would be really helpful if we could. So right here, value of X that maximizes density should be 1.51 after rounding to the nearest hundredth. Then this quantity is going to be the actual maximum density. That's a decimal there, so 4.13 after rounding. And now, last question they say is, for very large values of X, the density appears to, what would you say is the correct response here? Finite, increase without bound, decrease without bound?
Finite.
It'd be finite, absolutely. The reason we can tell is, let me see if I can get those things away. It's going to a finite value of 0. It has an actual horizontal asymptote. If it had no horizontal asymptote, we would have said either increases or decreases without bound. So really that's the answer as long as there is a horizontal asymptote on your graph. So let's click check just to double check if we've got everything in right. I always kind of cross my fingers with Alex. You never really know, but it looks like they're happy with that. Any questions at all, folks, with that topic there? Yeah.
So you're saying if there wasn't a horizontal asymptote that would have crossed the entire graph,
Mhm.
then it would be something that's like one of the other two options of it's going too high or too low.
Exactly, yeah. So if the graph say did something like this. Maybe it did a peak and then blew up. You would have said increases without bound. Exactly. Other questions so far? Okay. Well, that's the odd topic out of the ALEKS that we've been encountering. I think they're not getting too bad, but at least for me, that graphing calculator is kind of rough the first time you're working with it. It's a little bit easier as you go, but I would still personally use Desmos. It's just faster and easier to read the numbers on the screen. Well, we did example 5. Nothing really happens on the notes when we do these problems. And I always say this exact statement just as a reminder. These will never be exam questions because we don't have graphing calculators on exams, only reason. And this is where the last topics finally settle on. Just like with the polynomial equations, eventually we'll look at inequalities. And these are kind of just side topics. They're baked into ALEKS, so I feel like we ought to cover them. That's why I brought 2 examples here on getting through these kinds of questions. So these will be our last 2. We're solving an inequality, writing our answers in interval notation. And if we think back of how we did these in the past, we graphed these equations. That's because they were polynomial functions. Those are just easy to graph. These are not as easy to graph. These take a while. They take some time to put it all together. And so I want to show an alternative method on getting through this one. So if it's a rational function like this, the fastest, most efficient approach is to label this as an f of x function. So now that we have that as f of x, my first step, official step, is find the cut points. The cut points are, well, it's just like if you're finding an x-intercept or a vertical asymptote. First, focus on the numerator. You can get an x-intercept by plugging in -3. And so that's automatically a cut point on this one. Then if you focus on the denominator, you can get a vertical asymptote by plugging in +4. And that's the other cut point on this. The +4, it's kind of special as it stands. A -3, you can plug that inside this function, no problem. You get 0 = 0. And so it's even a solution. You cannot plug 4 in here. It's the equation of a vertical asymptote, x = 4. It's not in the domain. And so when you find those things that came from the denominator, it's a good idea to call it an excluded value. This will come in on step 2, and it's probably the trickiest thing about these kinds of equations. Any questions, folks, about getting those cut points? Okay, once we have the cut points, here's what step 2 looks like. We take an ordinary real number line, and step 1 is pretty much implying we're going to cut it up, and we really are. We put one cut at -3. Let's take a look at the inequality. Because it's greater than or equal to 0, what should we put here, a solid or an open dot? Good call, this ought to be solid. And this is conveying -3 is already one solution to this. Next, put in a cut point over here at 4. And this is really weird. This one's not a solid dot. We are forced to put in an open circle here, irregardless of the fact that it's less than or equals. It's open. Does that make sense to why, folks, that one has to be an open circle out of nowhere? Exactly, that's the best way to say it. -3 must be solid, and you can plug it in, get a solution. But if that's excluded, it's not even in the domain, plug it inside and you're undefined, that's never a solution to anything. So that's really wild. Watch out for these kinds of things. It's so tempting to put in a solid dot, but then I'd miss this question every single time in ALEKS, making it super frustrating. So this is the worst thing about this kind of problem. Now, after we've done our interval, or excuse me, our real number line, we're going to test 3 different intervals. I like to put these little decorations, -infinity and +infinity, in case it's part of the answer. And what we're going to do next is, I just need to see if f of x is positive or negative here, same here, and same here. So we're going to use test values. And that means we need to pick a number in this region. I'd say the most convenient number might be like a -4. That way the numbers aren't too bad. We're plugging a -4 inside of f of x. So f of -4 would be, first in the numerator, that's a -1. And the denominator will become a -8. And all I'm going to write here is bigger than 0. Just to emphasize, the actual value doesn't matter. It's the sign that matters. This is a positive quantity. So I'm going to put positive here. And now there is no potential for the sign to switch at all in this region from -3 going to the left forever. Always positive no matter what. So we rinse and repeat and test the next two intervals. There's often a switching here because these values, if we're setting them equal to 0, they came from groups that had power 1. So I'm anticipating a negative here and a positive here, but you know what's still a good idea? To really make sure. That way I'll know if I made a silly mistake, if I'm getting an opposite sign. So a good value here between -3 and 4, I'd go for a 0. There's no reason to work too hard, and 0 is working not very hard at all. F of 0 would be 3 divided by -4. We're just wiping out x's. That's less than 0, it's negative. So negative made sense right here. Let's test one more. At 5, we're plugging 5 up here. So f at 5 becomes 8 for the numerator, 5 minus 4, so 1 in the denominator. This would be a positive value. So I wrote greater than 0. I'm just going to put a positive sign right here. At this stage, you know what, we're pretty much done. You just have to decide which regions do we actually want, the positive regions or the negative regions. And it comes from this right here. Anyone see which ones we should grab, positives or negatives? Exactly, this should be positives. I heard someone. So I'll put here, we want positive regions. It was asking us to set that rational function greater than or equal to 0. It's equal to 0 here, but it's greater than 0 in this region. And it's less than 0, greater than 0 in this region as well. Now, again, this is a tricky ALEKS topic. Next thing I would probably do, put this into Desmos and see if it lines up. Let's double check the situation over here. Function I would put in is just what we indicate as f of x. So f of x equals x plus 3, x minus 4. And we had a cut at -3, and the curve should be above the x-axis to the left of -3. That's what we're seeing, and that's why we have a positive sign here. To the right of -3, it's below, all the way around to, where is 4 on this graph? Well, we're not going to put a 4 too easily because that's a vertical asymptote. But across 4, it's up here. It goes positive, so above the x-axis. And so if this sketch here lines up with your signs, you are on the right track. I would say take advantage of this tool. It helps out with the homework. And our goal is to be able to do it without any graphing utilities, so we're ready to go on exams as well. Last thing to do is just to summarize, I'd write the solution set equals, now we're just doing interval notation, grabbing just the positive regions. So it's -infinity up to -3 with a bracket. Then over here, take a union of 4 with a parenthesis. Let's highlight that in yellow again, because that's always pretty tricky on these kinds of problems. Follow the yellow as an explanation for why that's not a bracket on this thing. Goes off to infinity. And that's the whole shebang on this one. These are the kind of problems we'll see on these assignments here. Yeah, go ahead.
Is the value in the denominator always an excluded value?
Yes, it would always be excluded. Absolutely. And that means if you have greater than or equals, less than or equals, this trick will come into play, and we have to be very, very careful about it. But if it's this kind of problem, just a less than or a greater than, I'm still going to write that down as protection for when it's less than or equals or greater than or equals, but it's not an issue. Exactly, yeah.
Okay.
Other questions so far? Okay, well, we've got about 9-ish minutes so far. How about we try for one more and we'll call it a day after this? Does that sound all right to folks? Okay, so last one. This one's kind of terrible though. What made part A really nice is zeros on one side of the equation. This one's not so great. And if I try to multiply by x minus 1, I actually have a huge problem. If you multiply an inequality by a positive number, that sign doesn't change. I need to split this into cases and say case 1, x minus 1 is positive. And then I have to say case 2, however, when x minus 1 is negative, that sign does change. So if you clear the denominator, you're splitting into two inequalities that you have to solve. I feel like that's a more confusing approach. It's easier to do this, get 0 on one side, put everything into one spot and just analyze that function. Because multiplying a variable is extremely dangerous with these kinds of things. You always have to split into cases. Is the variable positive or negative? So let's start off this one by doing the first following steps. Subtract 5 from both sides, and we'll fix the issue and get 0 on one side. So it's 15. X minus 1 minus 5. I'll put less than 0 with a whole bunch of space. So this is what's going to allow us to solve the problem as efficiently as possible, getting that 0. But now we have to combine everything on the left-hand side. Can give a field promotion to 5, it's now a fraction. Then complete the denominator, it's missing x minus 1. Now we have the common denominator, and we'll just subtract across numerators. It turns into 15 minus 5, x minus 1, divided by x minus 1, the common denominator, is now set less than 0. Can do a quick expansion, combine like terms, and we'll have our f of x function like we had right here, which is what allowed the whole procedure to run through actually pretty fast for these problems. So 15 minus 5x plus 5 over x minus 1 is less than 0. And last step here to simplify this is negative 5x plus 20 divided by x minus 1 less than 0. Now this whole left-hand side, that will be the function f of x that we go to analyze. So kind of a nasty problem in a certain sense. You have to do preliminary work if you don't have 0. But once you have 0 on one side, now we can start the process. So how does the process start? Very first thing we need are the cut points. And we look to the numerator first. I mean, you could look to the denominator first, but you need a value of x that will make that 0. Anyone spot the value? 4 would do the job, absolutely. And there's no harm just taking that, setting it equal to 0 and just solving the equation normally. But yeah, put a 4 there, x equals 4 times negative 5, you get 0 above. So we can say the cut points are first one is negative 4. It's an ordinary cut point, so no danger there. Down below, you get a 0 by plugging in a positive 1. And so that's our next cut point at positive 1. And like we were mentioning, although it's not a trick question, it's still a good idea in case it becomes a trick question on your very next problem to remind yourself that's an excluded value. Let's put a note just right here. There is always an open circle here. So if you have an excluded value, no matter what the inequality says, there is an open circle on your axis. Kind of strange, but that's just because you cannot even plug 1 in the function. There's no way it's a solution. So now on step 2, we begin by actually cutting up the real number line. There's 2 cut points, one at negative 4. We'll put an open circle here to match the inequality. One at positive 1. Another open circle, because it's excluded, is probably the best way to think, just for the sake of being careful. Yeah, go ahead.
Positive 4,
Oh, positive 4?
so you divide by negative 5, -20 will be a negative.
Yeah, absolutely. And I think that's what you were saying as well. I must have just flipped my sign after running through and writing it down. Sorry about that. Yeah, put it in +4, just like you said, it's -20 plus 20 now. But that would make the denominator 40. That's way off. So let me make this positive right here. And thanks for spotting that. We would have detected it because when we do our sign chart, it's going to look really, really off. There's no way it's going to work out. So let me rearrange these things. There's one right here at 4 with an open circle and one right here at 1 with the open circle. Okay, I think that saved the problem. Thanks again, Cheyenne, for spotting that. Other questions at the moment? Okay. Last thing to do, and this is really just about it. Test values. And then state the interval according to the regions we actually want. Always use a different color pen. It's a good idea to write these kind of lightly because the test values are not necessarily part of where the intervals are going to end. The interval is going to end at a 1. Let's plug in a 0 and go f of 0. That would be a 20 divided by -1. So that means it's less than 0 here. And I'll put a negative sign in this region to convey that. Next test value, we can plug in a 2. So now we're testing this middle region. Let's see what f of 2 comes out as. That'll be -10 plus 20. 2 minus 1 for a +1. And yeah, this one is positive. We get a +10 altogether. So positive in this region. Now I'm anticipating a negative, but if we didn't fix where 4 goes, it's probably going to look wrong. I probably would have duplicated a sign and said to myself, that's odd. And it would have been because of that mistake right there. So that's a value in testing all regions. It can find a silly mistake if we make one. So let's try out 5 here. F of 5 is plugging in a 5 in this location. That'll be -25 plus 20. And 4 down below. Now, this one is definitely negative. This is -5/4 if we simplified it. So the negative sign here is appropriate. Next, because it says less than, it means we want the negative regions, which will be this one and this one. So all we now have to do is put in our answer. I'll kind of shade like this just as a visual representation of where the solutions are. But it's totally optional. What the ALEKS really wants, and I match that on the instructions as well, anytime we do this kind of problem, is the solution set in interval notation is now -infinity to the +1, union 4 up to that +infinity. So the 4 came from numerator, the 1 came from denominator, and that's the whole process for this thing. This one takes a little bit more time because of the preamble getting started. And if you're doing a longer problem like this one, again, treat yourself to some kind of graphing utility just to make sure the situation looks right. And you'll get through this ALEKS topic quicker than without that. Well, that's all I have for folks today. Any questions or comments at the moment? Okay, we didn't quite get to this section, but man, this takes a while to get through these functions. I didn't want to try to rush it. That would have probably been a bad idea. Have a great weekend, folks, and we'll be in section 5.7 when we come back on Tuesday.